So here's example 6.1. So it reads something like this. Far in space, where gravity is neglectable, a 425 kilogram rocket traveling at 75 meters a second in the positive X direction fires its engines. The figure shows the thrust. They actually called it a thrust curve. The thrust curve as a function of time. So a thrust curve means that you're plotting force versus time. The mass lost by the rocket during these 30 seconds is neglectable. So what do we mean by neglectable? So if the rocket weighs 425 kilograms and you only lose, let's say, 5 kilograms during this, 30-second interval, then we look at the percentage of 5 divided by 525. So if you look at that value here, that's going to be a pretty tiny value here. So if I look at that thing, what is that numerically? So if I look at that numerically, so if it loses 5 kilograms in 30 seconds, then that means that this is going to be 5 kilograms divided by 425 kilograms. And that numerical number is then 0.0118. So if you need more sig figures than this, then you have to include those 5 kilograms that were lost in the rocket fuel. If you don't, then we say that the rocket didn't lose any mass to a very good value. Now, here's what I want you to do. I want you to draw me a momentum bar diagram, sketch the situation and draw me a momentum bar diagram. And then we'll come back and we'll look at the impulse. Okay, let me give you a few seconds just to start looking at that, and then I'll get started. Okay, let's look at this thing here. So the first thing that I want to do here is that I want to interpret the situation. So what I'm going to do here is that I definitely want to sketch the situation. So let's sketch the situation and draw a bar diagram. So when I look at this thing, I imagine that I have a rocket. I mean, I'm sure you guys can do a better job with the rocket than mine. Look at that. It even has a cool stripe. Then I could see here that I got to give it wings. And then, of course, we have that wing right there. So since we're in make-believe land, we then have a rocket that's ejecting fuel that's on fire. So the one thing that I know here is that the rocket is moving in this direction. And what we're going to say here is that it has some initial momentum P1. Now, because momentum is a vector, I have to come in and I have to add signs. So in this situation, I'm going to say that my plus sign is in the direction of the initial momentum. Now what happens? The rocket's thrust goes. That means it starts to act. So what does the rocket's thrust do? Well, what it really does here is that it uses a concept of conservation of momentum, which we haven't done. But what it does here is it throws out exhaust in the back to make it go forward so that there's equal and opposite forces. But we're not talking about conservation of momentum. What we're focusing on now is that we come in here and we say, what is our system here? So our system is the rocket. But not the fuel. Isn't that crazy? So it's because if you say that the thrust is what's acting on the rocket, the thrust is not part of the rocket. So what happens in this situation then is that we would expect that the rocket is going to do what? It's going to go faster. So why does it go faster? Because there is an impulse. So I imagine that I'm going to have an impulse, right, that now causes this rocket to move faster. So just like the net force, the net thrust, the net impulse makes this rocket go faster here. So because of this, we see that before it starts here, afterwards, we expect that the rocket to go faster here. So if I come in here again and I draw my rocket, let me get a better nose. Well, that's not so good, is it? And then I have my wings, of course. And so if I start looking at my rocket here, what I'm finding here is that we expect the momentum to be larger after the thrust goes off here, right? That's what we expect here. So now that I have that, I could then go in and I can draw my bar diagram. So if I'm looking at my bar diagram, what do I actually see here? I see here is that I'm going to scale what I see with my picture. So again, look at my rocket. So when I see this, note that the impulse of the thrust causes the rocket's momentum to change. I can't talk about the momentum of a rocket at a single point. So then I'm going to come in here and I'm going to say, okay, so what was the momentum of my rocket? Well, my initial momentum of the rocket is this P1. Now, because of the way I'm scaling this thing, I'm going to say that this equals my positive direction. So this is positive, this is negative. What happens now is that the rocket applies an impulse. And we're going to say here that this thrust impulse is about this big. So this is the cause of the rocket's change in momentum. So what we see here is that the impulse does not disappear, but reappears as change in momentum of the rocket. The impulse doesn't disappear. It reappears. And so then if I continue to think in this way, then that means here's what I'm seeing here. So look at the initial momentum. It's this amount right here. This is the initial momentum. So now, when I look at that impulse, you could see that the impulse is 2 squares. So then this increases the momentum by exactly the same amount of the thrust. So therefore, this tells me here is that this guy is going to be P2. This is our mathematical equation. Okay. So now that I got a picture of what's happening with the rocket, I could now go calculate A. So then A says we want to calculate what is the impulse. So we need to calculate the impulse. So what does that mean for the impulse? Well, the first thing that I want to do is I want to go get a copy of the curve. So here's a copy of the thrust curve. Whoa, delete. I don't know what that is. Let me delete that. Here, let me go get this again. Apparently, I copied something that I don't know what I did. Let's try this again. This should be there we go. Here's my force thrust. Okay. So what do I know about this? For starters here, this guy is F max. We can see here is that from here to here, here's my contact time. What do I mean by the contact time? That is the time that the thrust is on, and it goes from 0 to 30 seconds. So we could see here that my contact time is that amount. So now, what are we trying to calculate? We're trying to calculate this area. So if I now go and I look at this thing, I want this area of this curve, right? This is what I want. I want that area. So when I calculate this area, this is what we call the numerical value of the impulse. So when I look at this thing, we could see here is that this is the area of a triangle. And what do I know about the area here? So if I look at the impulse, we said it has to be the area. And if this is a triangle, we know that a triangle is 1/2 times the base times the height, or the height times the base. It doesn't matter how you do this here. So now if I look at this thing, what do I really know? Well, what I know here is that the height of this thing is going to be the maximum force, and the base is going to be the contact time. So that's what I have right there. So now I could put in my numerical values. So then this will be 1/2. What's the height? The height is 1,000 newtons times the base, which is 30. So you could see here is that I have, that's 30,000. So 1,000 times 30 gives me an extra one. So that should be 30,000 divided by 2. This then gives me 15,000 Newton seconds. And this here is what the magnitude of the impulse is, right? That's our numerical value. So when I look at this guy, this is what I'm seeing. This is what we just calculated. Now, we should, we should actually look at this a little bit more careful here. So what I want to do here is that I want to copy this guy because I want to use this again. Now, if I look at the mean value theorem, for integrals, what it tells me here is that it says here is that the area, in this case, it's going to be a triangle, and we already defined this as 1/2 max times the contact time. This, by definition, I should be able to select the height in such a way that I get the average time force times delta t. In other words, when I focus on these two right here, that for a triangle, it tells me that if I come in here very lightly and cross out the times, you're seeing what this really gives me here is that the average force is equal to 1/2 F max. Isn't that shocking? That for a triangle, by the way, that is not true for a normal impulse curve. This is only true for a triangle. You can see here that I have a term that now allows me to calculate what the average force is. So picture-wise, what does this mean? What it means here is that I have this curve. Okay. Oh man, I wanted this other curve. Let me see if I can grab this and copy it down. Let me see if I could put this in here. I want it, no. Let me try one more time. I want the whole thing. Okay, let me delete this whole thing. So picture-wise, this is what I'm trying to show you. Damn, are you kidding me? Okay, let me get rid of this then. This isn't working. Sorry for wasting your time. So when I look at this curve, what does this really tell me? Well, for starters here, it tells me that this guy right here is how we calculate the impulse. And because the impulse is triangular in shape, we know what that numerical value is. So what we're seeing here is, again, this here is F max. This right here is my contact time. Well, the mean value theorem says what? The mean value theorem says I have a curve that I can create. And this curve also has 0, and it's going to go all the way 1, 2, 3, 4, 5. It's going to come all the way to here, which is 30 seconds. So when I look at this guy, I can create a second curve that has a height. So if this height right here, let's look at this. So if I scale this, so if this is F max, then I'm going to try to pick half that value, which I'm assuming is going to be about right here. So this is going to be the average value. And if we calculate the average value, it's got to be 1,000 divided by 2, which would give me 500. So then I have a curve that I can draw that looks exactly like this. And when I calculate this thing numerically, so we know here that this numerical value here is 500 newtons. And we can see here that if I calculate this area, that then the area is then going to be F average times my contact time, which will be 500 newtons times 30 seconds. Note that I get exactly 15,000 Newton seconds. That's what the mean value theorem is telling you. So this second result of the mean value theorem is really, really powerful. And it's actually quite sexy. And the reason why I say that here is because it's really nice. It could make things work considerably better conceptually as well as mathematical, as long as you're able to do that. So now, let's go back to part B. So now that I've calculated the impulse, let's look at part B. And here's part B. So what I'm going to do here is I'm going to make this thing, and it says here, at what time does the rocket reach its maximum speed? So again, here's my curve. Right? Here's my curve. At what time does the rocket reach its maximum speed? Is it at F max? Right? That's where the rocket is going the fastest, or it has the maximum force. Is it at 10 seconds? Or is it at 30 seconds? The answer is that it's at 30 seconds. So the answer is it's at 30 seconds. And the question is, why? Well, what I'll do here is that I want to give you an analogy, okay, to try to conceptually get you to think about this. So the analogy that I want to do here is, let's say that you're going to push a car. Okay, you're going to push a car to get it a push jump. And we talked a tiny bit about it, but I'm not going to go into the details what a push jump is. So what do I know here? I imagine, as usual, let's say that you're nice and fresh. So we have our car, okay? And today you're feeling orange, so you're driving your orange car. Right? Here's your orange car. And what you're going to do here is that you're sitting in your orange car, and as usual, you get a sucker to push your car. Now, if you're going to push your car, you want to get somebody that's fresh. So if somebody's fresh here, what you're going to find here is that they're going to get back here and they're going to start pushing on the car. Like, you should get your girlfriend or your boyfriend to actually push your car. And then, of course, if they're not pushing hard enough, you got to say, come on, push harder. Right? You want to get that jump start. So now, let's say that you're moving at some speed 1 right here. So now what's going to happen here is that now look at the curve. So here, we can see here that the curve, it starts with F equal to 0. And so what you're seeing here is that over time, it reaches a maximum force. So you push hardest from 0 to 10 seconds to get max force or max push. So you could imagine that when you get to 10 seconds, you have now created a force that's going to give you a maximum force. So now what happens? You've been pushing for 10 seconds, so now you're tired. So what you're going to see here is that after 10 seconds, according to the thrust curve, your strength starts to decrease. So what does that mean? Are you still pushing? Yes, but you continue to push. Is the car going to go faster? Absolutely. The fact that you continue to push, that means you're going to be increasing the speed of the car all the way to 30 seconds. So now your speed continues to get faster, even though your force now is smaller. So this thrust curve is telling us that at 30 seconds right there, you get max speed because you continue to push. So that being the case here, and we kind of look at this thing. So now what I want to do here is it says at what time does it, at what is the maximum speed here? Well, what I'm going to do here is that to calculate max speed, apply the impulse momentum theorem. But wait a minute, we've already done that. This is what we were setting up right here, right? Here's our impulse momentum theorem. So if I come in and I look at this thing, here's my impulse momentum theorem, and we've already drawn this. We already know what's going on. So what am I going to do? I'm going to use my drawing to write out my picture here. So then from my drawing here, I'm going to say that the bar diagram is a mathematical representation of an equation. So in other words, it reads that I have a positive P2 must equal a positive P1 plus a positive impulse due to the thrust. And then if I continue to write my stuff in here, what do I see? I can rewrite this as the mass of the rocket times the velocity 2, the mass of the rocket times velocity 1, plus the impulse that we calculated for the thrust. So now, if I solve for max speed, which we now define as V2, you could see here is that I'm going to divide both sides by the mass. So I'm going to get V2, V1 plus 1 over the mass times J of the thrust. So now if I start putting in my numerical values, we see here that from the question, it says that V1 is 75 meters per second. We know that the mass of the rocket was 425 kilograms. And finally, the thrust that we calculated was equal to 15,000 newtons per second. So if I plug in these numerical values, what we're seeing here is that the initial speed of the rocket was 75 meters per second. What did the thrust actually do here? It added 35 meters per second, right? So when I look at this, this is the increase in speed due to the thrust. So when I look at the overall number here, we can see here is that this is 110 meters per second, and that is the final speed of the rocket, its maximum speed.